Now let's go through the entire exploratory data analysis process with example data. And this is actually real data from carbon dioxide measurements from the top of the Mauna Loa volcano in Hawaii. And this data actually consists of the longest record of direct measurements of CO2 in the atmosphere. So let's start with the first part of the process, which is to understand what you have in the data. And to do this, first you want to start if there is a file description available for your data. That's your starting point. So let's jump over to the notebook and take a look at the data and the file description. So we are in the Exploratory Data Analysis Jupyter Notebook, and this is in the EDA Visualization folder. And in particular, we're going to jump down to the part of this notebook that starts with data faithfulness. So this data is actually coming directly from this link on NOAA's website. This is data from their Global Monitoring Laboratory. And in particular, you can read a very in-depth description of exactly how they're measuring these background CO2 levels. So this is very useful background information as to what the data is. So you can take a minute and read this. And then you'll also see that there are some plots if you go to interactive plots, and we're actually going to recreate these plots once we've cleaned up the data and loaded it in. So we'll be moving towards getting both the red curve and the blue curve here. This trend as well as the CO2. But we need to load in the data and explore it a bit and clean it up. So this data is in a text file that's in the data folder here. And before you just go click on it, which you can here, I find it to be good practice, and this just jumped, there we go, to actually check the file size before you try to open it so it doesn't inadvertently cause your system to crash. And so here are some quick ways you can do this using built-in Python tools. This is telling me that the total file size is 0.05 megabytes, so it's small and it only has 810 lines. So this is definitely something we could just glance through. So I'm clicking on it now. And I want you to take a minute and put this on pause and read through the description of the data. So you want to start here and then go through to line 72 or 3, where you also glance at the beginning of the data to start to get a sense of what it is. So go ahead, put this on pause, and then we'll come back and summarize what this data represents. So as you read in the file description, each of these measurement variables, which are average, interpolated, and trend, are the monthly average CO2 mole fraction determined from daily averages. Okay, that's a lot. Let's unpack that. So the monthly average CO2 in parts per million, so that's our number of CO2 molecules per 1 million molecules. We're computing that from daily averages. So each day we get an average, and then we use the daily averages to get our monthly average. And you read in the description, they calculate the average one, then they calculate an interpolated one to use, especially when you have missing data. And they capture an overall trend, and they use this trend when calculating this interpolated column. All of that is described in the text file description in more detail. Then we have the number of days, and so that's the actual number of days that the equipment worked in a given month. And we'll see this -1 is, there's not -1 days, this is a stand-in number to let us know we're actually missing information for at least these beginning months here. And then if we look at the first 3 columns, this one, and this one, we can notice, well, the first column is year, the second column is the month of the year, and then the third column is actually the date in decimal. So this is the first step in the process, is just figuring out what data do we even have, what do each of our columns represent. And now let's go into reading in this data into a data frame, creating column names, because you can see we're missing column names for the first two, and making sure we have everything in the right format to be able to analyze the data. So how do we read this text file into pandas? First few things we're going to notice just looking at the first few lines of the data, we can come back to here, is the data is separated by white space, not by tabs. The first part of the relevant data gets loaded in at line 73. We have some headers around line 71. And the data line up down the rows. For example, the month appears in the 7th to the 8th position of each line, right? So that's what we're seeing here. This month is showing up either in the 7th, there's the 7th position, or there's the 8th position. And I'm counting positions by just going over here and doing spaces. 1, 2, 3, 4, 5, 6, 7. All right, so it turns out Read CSV can handle this type of data. And basically we're going to need to specify a few things. That there's no header. We're going to need to specify that we want to skip down the rows until start on line 72 to read this in. And then we're going to need to explain that we have continuous white space. So the separators are white space, not tabs. So to do this, as a reminder, you can click on this and go over to the documentation for Read CSV. And in particular, we're going to use header, we're going to use separator, and we're going to use skip rows right here. Okay, so let's put all of these together. And I've named this up above. You don't have to do this, but I've named CO2 file this file path. So I'm going to call CO2 underscore file. So I have PD read CSV, and then I would like to read the CO2 file. I have header is equal to none. I'm going to say I want to skip the first 72 rows. And then my separator. So this last piece is actually using what's called regular expression syntax. This is out of the scope of this class, but I'm going to put it here just so you can see. This right here is telling us that you have, I'm going to put it, this is regex delimiter for continuous white space. Okay, that's letting us know that that's how it's separated, is by continuous white space. Again, you can pretty easily do a quick Google search for whatever regular expression information you might need when reading in files in the future. All right, so this is a good first step, but notice our columns are not named. So now we need to do more EDA. So I can actually do one more step, and if you look back at the Read CSV file or Read CSV documentation, there is an input called names here, which you can use to name the columns. So that's what we're going to do. I put everything that we had just before, so these are all the same ones, and then I added names, and I put the names of the columns. So I knew the first column was year, the second one was month, decimal date, then I'm just calling it average, interpolated, trend, and days. And now, this is looking good. Okay. So the next thing I want to check is that these got read in as the correct data types. So yes, year and month should be integers, decimal date. The rest of these can be floats. And so everything looks good. We don't have them incorrectly read in as an object. And so far everything looks good to continue going forward. Now, we can start by trying to visualize what this average CO2 monthly column, so this average column, looks like over time. And I don't want you to worry so much about the code here, because we're going to cover this in our next video when we talk about visualizing data. This is using the Seaborn plotting library to plot this information. Here we go. But yikes, you can see already that we have some, normal looking things, and then we have these drastic spikes where we have values of negative 99. Okay, so let's dive into what happened. Let's look at the first 5, and then the last 5. And we can see that, some of these columns have unusual data points, or data values, like negative 99 or negative 1. And if we look at the description at the top of the file again, so let's go back to here. We can see that negative 99 is their code for missing data, and negative 1 is their code for missing data in the days column. So let's decide how we want to fix this. Before we go into deciding what to do with this missing data, let's explore other aspects of the data so we get a better feel for what we're working with. And it's always good when you're working with time series data like this to do some sanity checks and decide, well, if we have data from March 1958 to August 2019, we should have 1 record per month. So we should have 738 records, and we can quickly check that by looking at CO2.shape, or you also could do length of CO2. And we can see that the number of rows match the expectation, so that's a good sign. Let's dive a little bit deeper. Let's look at the days field and times, right? Or we'll look at days and months and figure out if we're missing any records. So first, let's dive into our number of months. And if we want to break this out by year, let's actually look in the month column. So we'll do CO2 month. And then I would like to get how many months I have. So we're going to do value counts. So how many entries I have for each different month value. Let's do that first, right? So this is, I have 62 entries for March, 62 entries for April, right? And then 61 here for September, for October, for November. We can also do it by sort index. It's just so we can get them in order. You can do it either way. But if I do sort underscore index, now they're in order by here. And as expected, this looks good. January, February, September, October, November, December have 61 occurrences. The rest have 62. So this is good because we're not missing records in any of the expected months. Now let's look at days. And we're going to plot this. I'm going to look in particular at the distribution of the days column. And so we can see that we have, most of the days here are between 30, between 25 and 30. But then we actually have a huge number, almost 200, where we're missing data. And remember, days was the average number of days on which the measurements were taken. So the average number of days the machine was, or the instrument was correctly measuring CO2. Let's figure out if there's any pattern about when these missing days occurred, and we can do that by doing a line plot. So actually, let's do a scatter plot. That's better. So why did I not want to do a line plot? Because I'm going to have, for a given year, I have 12 data points for each year, because in each year there's 12 months. And so if I did a line plot, it's not going to work at all because I have not a functional relationship here. This is for each input, I have 12 outputs. So scatter plot is our go-to in this. And you'll notice that all of the missing years actually occurred in the beginning, like roughly the first 15 years is when we had missing data for that days column. So this tells us either maybe they decided 15 years into the project to start keeping track of the number of days in the month in which the instrument was working. Or maybe there was just problems. They didn't have a way to measure that early on. So based on this, right, we can see once they started tracking the number of days per month in which this instrument was working, they had pretty consistent values here between, roughly between 20 and 30 days in the month. And then you have some outliers here, the mid 80s, where maybe it's not doing so well for a few months. Or maybe here we had not so great couple of months. Okay, so what can we do with this? One thing would be to do some confirmation, look further in the data on the website to make sure that that's true. And then it's because it seems like maybe they just decided not to have this measurement or this column recorded in the beginning, we could probably drop these earliest recordings. But again, before you drop anything, you really want to examine overall trends to decide if dropping the data is going to cause any, introduce any unintended biases or things into your data. So that's our first missing value. The second missing value were these negative 99.99 values in our average column. So again, let's look at a distribution of those. All right, and we can see overall it's a very small percentage. It's actually, I think, only 7 measurements here that we're missing, less than 1% of the values. Let's actually see exactly which ones are missing. So take a minute and based on what you know from our Pandas Bootcamp, write code that is just going to select the rows in the data frame where this average column is equal to negative 99.99. Go ahead, put it on pause. Okay, so I want to look at all rows where my average column, and I'm actually just going to search for where it's less than 0. You could also do equals 99.99, but it's just faster to say less than 0. This is just going to give me, if you recall, a Boolean output, but I actually, to select the rows, I need to put this as the input here. So I put this in brackets, and now I will get the actual rows out. I won't get just a Boolean series. Okay, so we can see it's these 7 months, and there doesn't seem to be a pattern to this other than, most of these records are also missing the days data. Okay, so now we can think about what do we want to do with this missing data. And in general, 3 possible things you can do is decide to drop it, or set it to NaN, or do some type of imputation, which is like replace that number with a different number using some strategy that seems reasonable. Again, our goal is to try to fix this plot where we have these crazy spikes here. So let's actually examine what happens if we use each of these 3 different strategies, and then we'll pick between those. So if we want to talk about dropping the missing values, let's first create a data frame that only consists of the values that don't have negative 99.99. So this is going to look almost identical to what we did above, but I just want to select the ones where average is greater than 0. All right, that's going to get me a new data frame where I've basically dropped the missing values. Another way is I could replace and I'm going to word this differently. We're replacing negative 99.99 with NaN. Okay, so take a minute, put it on pause, and see if you can do that replace statement here. So there is a built-in replace method, so I can do replace. I put what I'm going to replace, so negative 99.99. Anytime I get that, I'm going to replace it with NaN. And that will give me a new data frame with everything replaced. So I'm running that. And then the third option is to substitute it with a likely value. Sometimes you'll substitute it, for example, with the mean or the median, but we actually can do even better than that because our data set actually comes with a substituted value. That's what that interpolated values column is. They've done some detailed behind the scenes math to come up with a substitute value for missing data in that column. So that's the other thing we could do, is just use the interpolated column. So take a minute here and try to write some code where you now have a data frame that uses the interpolated column just for the cases when you had missing average values. Okay, so a nice thing about how they created this is they created the column interpolated to actually have values that exactly match those in average, except when the average is negative 99.99. So they've already done all the work for us here. So I am going to make a copy of the entire data frame here, and then reassign the average column to the interpolated column. Okay, and I made that copy first so that I wouldn't overwrite my original data frame. All right, so that's the third option. Let's plot these, and I'm just going to zoom in on the measurements in 1958 because we know we have 2 missing values in that time period. And this plotting code, again, is not in the scope yet because we haven't covered it yet, so you can just run it, and you'll see that we now have 3 different ways of addressing this missing data. So when it's set to NaN, the missing data here that happens in June and in October, you just see gaps. When we drop it, you'll see what happens is that we basically just connect the line between these 2 data points as if there was nothing in between. And then the interpolated one is actually giving the best guess, the best interpolation based on the overall trends of the curve. Okay, so in this case, because there's only 7 values that are missing, really you could pick any of these 3 approaches. Any of them would be reasonable. But I would say that out of these 3, there's really some appeal to doing this imputation because that helps us still see the seasonal trends. And that way we're plotting all the months in the data as a line plot, as opposed to skipping some here or just having some gaps. So based on that, I would choose this option. But again, you could make an argument for any of these 3 given this data set and the small amount of missing data in this case. So now let's replot this original figure using the interpolated values instead. Aha, and we can see we get something very close to what we originally saw on the NOAA website. So we have read in the data, done some wrangling, cleaned it, and have been able to recreate that plot. So here's a summary of what we did and a summary of our updated plot. And just to point out, with numeric data, we're generally doing this wrangling process as part of the EDA, and that's what we saw in this case. Now let's return to the notebook to actually have a follow-up discussion on granularity. Because right now you can see we're presenting the data at the level of granularity that we had in the original file, which was at the month and year level. So we have data for a specific month and a specific year. And we're able to see this seasonal variation that's happening just due to the change in the Earth's vegetation as the seasons change each year. That's what you're seeing by this ups and downs, ups and downs, ups and downs each year. But then overall, we also have this overall increasing trend. And so let's talk about how we can capture that overall increasing trend by adjusting the granularity. So right now, we have been looking at average monthly data, but we might be interested in capturing this overall global warming trend that we're seeing happening. And so if we wanted to capture that coarser granularity, I want you to take a minute and try to write some code here that's actually for a given year, right? Instead of looking at each month and tracking all of the monthly measurements, let's average out and get for a given year just one measurement that's the average of all the months. So see if you can use what you know about group by to get a coarser granularity here. So take a minute. All right, so we're going to take our imputed version, right? That was using the imputed values, and we're going to group by year now. And then we'll just take the mean. And before I plot that, let me show you what's coming out here. Right, and so that now is giving me the the mean. These are means in each of these columns. So the mean month, this doesn't make sense anymore, right? But this is now the average of the average for the 12 months, the average of the average for the 12 months. So this is what we're going to now plot. And that's what you can see here. And when I do this, this smooths it out. This gives us the other plot that we saw on the original website, which was showing this overall trend, getting rid of the seasonal variation. And so we do see a rise by nearly 100 ppm of CO2 since this began the recording in 1958. So this data is capturing this very noticeable trend. So let's summarize the steps we went through in this demo. We started by looking at the data and the metadata. And then we looked at what each field represented and the granularity of the data. Then we looked for some related dimensions. So in our case, we were looking at trends by year, but sometimes you want to do things depending on your data. You might want to break down grades by major, etc. And then along the way, we were visualizing and summarizing the data and validating assumptions. So we were going through to make sure, did we have data for every month we would expect? We were paying particular attention to when we had missing data. And then we chose ways to identify and address anomalies and missing data. Sometimes you'll also be applying data transformations or corrections. In our case, it was already built in. It was supplied to us in the data file, but sometimes we'll have to choose on our own how we would like to impute or replace missing data. And then I would really suggest that in this process of EDA that you really keep track of what you do along the way in each step. And a great way to do that is to do all of this through Jupyter Notebook, because then your work is reproducible and it's easy to go back and make any tweaks as needed. One aside at the end of all of this is we looked at data up through 2019, but actually there was an eruption of this volcano and they had to suspend observations for about 6 months. They actually moved the sensor to a nearby volcano and then resumed after the eruption had subsided. So this didn't affect the data we looked at specifically because we stopped in 2019, but this just highlights the importance of being very aware of where your data comes from, where there might be any anomalies or changes in the instruments that are used to measure your data, because that can definitely affect any conclusions you make from the data. So this was one example and one overview of the EDA process.